Dr. Mir Faisal. Dr. Mir Faisal did his master's from the University of Durham in the UK in physics, and then did his PhD in physics from the University of York, specializing in quantum gravity. After that, he did postdocs from the University of Durham and also from the University of Oxford. After that, he has been the scientific director of the Canadian Quantum Research Institute, and also he is teaching at the University of British Columbia in Canada. He has published over 174 papers in various journals, including Nature. He has an H index of 41, an I-10 index of 118, and also he is in the top 2% of scientists in the Stanford list. And his work in physics spans a broad range from string theory and loop quantum gravity all the way to condensed matter physics and also astrophysics. So it is an honor for us that he has joined us for this online lecture, and I hope it will be a fascinating talk. Before we start, I encourage you all to please turn your mobiles to silent mode so that there is no disturbance during the talk. And after, he will first of all give us a presentation. He will present some slides, and after that we can have a Q&A session. And during the Q&A session, first raise your hand, and then the mic will be provided to you, and only then ask your question. So let me hand it over to Dr. Mir Faisal. He will first give a presentation, and then we will have the Q&A session. So let's welcome Dr.
So are we live now? Or yes. We have been live already?
Yes, we are live. We are live. You can begin the presentation.
Great. Yeah, you never told me when we are coming live. Okay, great. So,
yes,
So I'll be talking basically about physics beyond space and time, even though I would have preferred a different title for it. Cosmism was my favorite title, but then it was suggested that might not attract a lot of audience, so make the title more interesting. So I thought, well, this is a good enough title. So basically, I'll start the journey of physics in a historical context and see where we have ended and where we started. Again, pre-Newton, there was a lot of physics done, but we had to start somewhere if I don't want to spend all time discussing ancient and medieval physics. So let's start.
Can you first unshare your screen so that the audience can see you first a little bit? Can you bit first, then you can share your presentation.
So audience, I'll unshare my screen. Hi audience, this is me online, and now I will share the screen, the more interesting part. Yeah, they can see me also during the Q&A session. Okay, now screen. Yeah. Okay, great. Let's go back to this. So I think we have to start somewhere. So I think Newton is a good place to start. So let's start from Newtonian physics. So and the important thing is that I will follow the advice of the editor of Stephen Hawking. I won't use any equations in here. And even though I'll be discussing things which are really complex, I have tried my best to really simplify it. So it will be sometimes oversimplified, hopefully understandable to everyone. And if something is not understandable, please let me know. I will try to explain it better, and we can also discuss it further in the Q&A session. So in Newtonian physics, what is physics? Basically, you have space and time as two independent observer-independent concepts. So what does that really mean? So you have a fixed length, say between 2 points. This length remains the same for anybody, any observer. It does not depend on who is measuring this length. This length between 2 points remains the same. The same thing at time interval between two events. It doesn't matter who is observing it. It does not. It's not in Newtonian physics. It does not make sense to say, between now and me going out of or this lecture lasts for 1 hour, but you can't really say 1 hour for who. 1 hour for you is 1 hour for me. That is how Newtonian physics works. And then universe is made up of material particles which basically move due to the action of forces, gravitational force being one of such force, and that is all that is to reality. That is it. In Newtonian mechanics, that is it. So, and space in itself is three-dimensional. What does it mean to say space is three-dimensional? Take any point in space, you can draw three perpendicular lines, three lines which are at 90 degrees to each other. So you have three directions to move about. So with this, with this observation, what do we come to? Philosophically, we come to something very interesting. Now, if you know precisely, in principle, it might not be, I don't think it's in practice possible, but you say in principle, you know the position and you know how the exact location and exactly how fast any of all these particles are moving at any point in time, then you can predict exactly where these particles will be at any later point in time and where these particles were at any previous point in time. And in Newtonian physics, since space and time and matter moving in space and time is all that is to reality, you can basically know everything about the universe in principle. And this view is called Laplacian determinism. So everything is fixed. There's no free will, there's no nothing. Everything is fixed. Everything is just motion of particles moving in space and time. And this view, and the philosophical view which develops out of this idea that all that is there to the universe is space and time as two independent concepts, and material particles moving in space and time is called materialism. Basically, all that is there to the universe is material particles moving in space and time. Well, these are some nice references. The first one is a philosophical reference on Newton's view on space-time, and the second one is the third one is a really nice mathematical book introducing Newtonian mechanics or classical mechanics in a more nice mathematical formalism. Basically, it's just Newtonian mechanics dressed up in mathematics. And the last one is a philosophical reference on origins of materialism. Now, this view starts slightly changing when you come to spatial relativity. Why? But not drastically changing, but slightly. Because in spatial relativity, lengths between 2 points and time interval between two events is not something that is universal and observer independent. So time length for me would not be the length for you if we are moving at really high velocities. And by high, I mean velocities comparable to the velocities is a physics technical term for speeds, very high speeds. I will make it really simple. Very high speeds, the speeds comparable to the speed of light. But however, you can do something else. You can construct a new physical quantity called a space-time interval. You basically take length, take time, mix them up mathematically, you construct this new physical quantity called a space-time interval. And this space-time interval is again same for all observers. So this really means that what we were observing as two physical quantities, space and time, are not really two quantities. They're just parts of a single quantity, single physical quantities, which we should call as space-time. The only thing why we observed them as two independent quantities was because we're moving at very small velocities or speeds relative to each other. And the mixing of space and time becomes really small at such scales. So you can effectively consider them as two separate quantities, even though in reality they're just one single physical quantity. This also has deep consequences for other things in physics. So everything that depends on space and time, everything that depends on space, any physical quantity that depends on space, has a temporal, has a time part of it. So so there is an equivalence between energy and something called momentum, which is basically something called velocity multiplied by mass. But basically, every physical quantity that has a spatial part has a temporal part to it. And in fact, this is the main observation which mathematically produces the relation between energy and mass that has been really popularized. So I hope I'm going simple enough. Again, some nice philosophical references on spatial theory of relativity, something that would benefit general readers, and space and time, and some really nice physical reference on top about spatial theory of relativity. I just thought I'd give references to everything I say, because I'm going to say controversial things at that, and I need references for that. So now look at this. You can have something which is flat, like a flat piece of paper, but you can take this piece of paper and make a ball out of it. You can curve it. In spatial relativity, even though space-time is four-dimensional, you have three components of space, one component of time. It's flat. General relativity says no. Actually, space-time curves in presence of matter. And gravity that we observe in space and time is nothing but the curvature of space and time. The gravity that you observe is nothing but the curvature of space and time. So this makes gravity really special. Whereas other forces move in space and time, gravity is the very geometry of space and time. So again, space and time is not a fixed background in general relativity, it's dynamic. It has a geometry, and this geometry is fixed by the matter that is present in it. It is determined by the matter present in this geometry. So that's a very interesting idea. There are, I have to specify that there are general theory of relativity is not the only theory of gravity at present. There are tons of theories of gravity called modified theories of gravity. Again, in question answer session, if you want to ask me, we can discuss this. This is a really interesting topic and a very interesting topic for research also. There are tons of different theories of gravity, but what all these different theories of gravity have in common is that gravity is the geometry of space and time. I'm not here even saying curvature of space and time for very good reasons. Question answer session, if somebody asks me, I'll tell you why. But now the important point here is that neither general relativity nor any modification of general relativity, any modified theory of gravity changes the concept of materialism. Because now instead of material particles moving in space and time, we have material particles moving in space-time. That's it. Some really nice references again on general theory of relativity first, and then some on modified gravity. I just stuck in my essay here, my DRF essay, which got honorary mention, because this will tell you why I did not use the word why I use the word curvature. Why I use the word geometry of space and time rather than curvature of space and time for modified theories of gravity. Yeah. Now coming to, but now that's so far so good with general relativity. Now we come to something more interesting, quantum mechanics. Now see, in general relativity, in special relativity, all it stated was that you can't measure like the space the length or time don't have observer independent meaning, but space-time does. That's it. General relativity made it dynamic, but still it had observer independent meaning. A space-time interval for one observer was the space-time interval for any observer. Quantum mechanics changes that. Quantum mechanics states, at least in the Copenhagen interpretation, that the very act of observation changes the physical state of a system. And this is very important. The act of observation cannot be represented by a physical interaction. It is really the idea of taking information out of the system, which will be very clear in the next slide. So in quantum mechanics, but the important thing is in quantum mechanics, material particles still remain material particles. It's just not possible to predict their exact location and how fast they are moving exactly. But you remember that I told you Laplacian determinism was based on the idea that if you exactly know the position of every particle in the universe and how fast it's moving, you can basically know where it will be at any later part in time, or however it will be at any point of time and where it was at any point of time in past. So, but you can't exactly know the exact position and momentum or position and how fast a particle is moving in quantum mechanics. And it's not a technological limitation. This is how nature is built. In nature, it's not even possible. It's not even sensible to ask how fast a particle is moving after you have exactly fixed its position. And the same thing holds for energy and time, by the way. You can't know what is the exact energy of a particle and at what point this energy was measured. So this really destroys Laplacian determinism. Laplacian determinism has no place in quantum mechanics. I will not dwell deeper into measurement problem of quantum mechanics. Why? Because there are other approaches to quantum mechanics. For example, there's an approach called objective collapse. It's called objective collapse theories, where the wave function actually collapses. Of course, it modifies quantum mechanics in a way. Now, these modifications are small, and it again they also coincide with all the experimental data we have. It predicts small deviations from quantum mechanics, but these deviations have not been experimentally verified. But the important thing is that there are other approaches to quantum mechanics. Objective collapse models being one of them, environmental decoherence being other, and then there are a set of other really interesting approaches to measurement problems. This is again something interesting if people want to do research. Lift a quantum phenomena, see the effect of objective collapse on those on that phenomena. There's one model of quantum mechanics before I go ahead that I have to strongly criticize, and it is the many world interpretation of quantum mechanics. Now, many world interpretation should not be confused with multiverse. Again, there are many ideas of multiverse. Please ask me a question about this because I don't have time to explain this in the slides. I would be happy to discuss how there are different models of multiverse, how some of them can even be experimentally falsified or tested. But these are decent physical theories. What is really strange and what is really, I would say, bad physics and bad philosophy doesn't make any sense is the many world interpretation of quantum mechanics. And if someone asks me, I think I have a thought experiment to show that nobody really believes in the many world interpretation of quantum mechanics, even if the people who are writing papers on it. Again, something I'll leave for the question session. Some nice questions people can ask me. I'm giving you questions from here only that I would love to answer. So this is some interesting work. Again, some references on the different philosophical consequences of quantum mechanics. This nature and the Copenhagen interpretation of quantum mechanics, and then the 2022 Nature paper is on objective collapse models, where the system actually collapses independent of the observer, but it is a small modification to quantum mechanics, and how this could be tested. And then you have the last paper again about foundations of quantum mechanics. There's the various approaches to foundations of quantum mechanics. Now, why is quantum mechanics really special? Why? Oh no! What did I do? I did something stupid. Okay. Go to downloads. Yep. Okay. Yeah, that shows how good I am with technology. I started as an engineer and I changed to physics, and that you can already understand why. So let's go back to this. So quantum mechanics. We did quantum mechanics. Let's see. Double slit experiment. That is where we are. Double slit. So I'll tell you how weird quantum mechanics is, and I'll go beyond the usual double slit experiment. There's a reason why I said double slit in space and time. So anybody who knows basic quantum mechanics knows about double slit experiment. You have two slits, basically two holes in a wall. And if you throw a jet of particles towards these holes, they will form a certain pattern. If you throw a wave, like a water wave, towards these two holes, the waves will form a different pattern if you measure them after they pass through these two slits. That's well known in classical physics. What happens if you take a quantum particle? Well, if you take a quantum particle, if you do not try to measure which slit the quantum particle goes through, then it will form a wave-like pattern. And if you try to exactly obtain the information about where this particle has gone through which of the two slits, then it will form a particle. Then it will form a particle-like pattern. So if you know exactly which slit the particle has gone through, which way information, it's called which way information, which way did the particle go, then it will form a particle like pattern. The important thing here is that this will hold true even if you throw one particle at a time. And the real question is, how did the future particle know that the past particle, you had made a measurement of the past particle or not? A strange effect. The effect starts becoming even more strange if you use a quantum eraser. Now what happens? Now this is the important thing. You throw a particle, you know you do something from which you can actually know the information. Information relating to which slit the particle has gone through. Now it has already passed through this slit, but you do something else to it and you erase this information. You erase the information about which slit the particle has gone through, and it again goes back to forming a wave pattern. So but it could only have interfered at the point at this double slit, and you have erased the information after it went in the double slit as a particle. How did it again become a wave and interfere? Did the particle know that you were actually going to do this experiment in future? It keeps becoming weirder. There is a experiment. It's called a delayed choice quantum eraser experiment. And what happens with this delayed choice quantum eraser experiment is that you make a measurement in future. You have two particles, two entangled photons. On one of the photons you make a measurement in future, and it affects the result in past. It's like the past particle changes its behavior because something is going to be done to its partner in future. That is really strange. Something changes in past because you're going to do something in future. And this thing has been even observed in 2000. And this was, by the way, published again in Nature Physics. There's a 2023 Nature Physics called the temporal double slit, where they did a double slit experiment in time, not in space. You can have two slits where in space you have some space where particles are allowed, and then you have a space where particles are not allowed, and then you have a space where particles are allowed. You can do the same thing in time, and you again form interference patterns. The important thing is, how on earth did the particle know that you're going to stop future particles, and why did it change its behavior now? Because you're going to you're going to create a double slit in time. These things are mind-boggling. This really shows that quantum mechanics, there's something really deep about quantum mechanics. It's not just balls hitting balls. There's something really more deeper going on here. And in fact, to give sense to these ideas of delayed choice quantum eraser experiments, concepts like retrocausality or superdeterminism have been proposed. So what is retrocausality? Well, people have argued it's not causality, it's retrocorrelation. But in any case, the idea is that future affects past. Causality goes like cause gives rise to effect. Well, no, maybe effect gives rise to cause. It's not, and that's why it's called retrocausality. There's an alternative view. Again, I don't subscribe to this view. But this alternative view says that human free will is a part of nature. So nature not only fixes the behavior of particles, it also fixes your behavior. And so somehow it knows that you're going to do this experiment, and therefore the particles change their behavior today. It is interesting. I have a different view to this, which will be supported by acosmism, which I think is more natural than superdeterminism. But you can see that why these views have come up. One important thing here is that I don't think quantum mechanics. Did I miss that point? Yes, I think I missed writing a point, or I've written it somewhere. But the important thing here is, let's see, in quantum mechanics, material particles still remain material particles. We don't know about their behavior. And so I don't think quantum mechanics, even though it has some deep things to say, you could still somehow argue for materialism here, at least in some form, even though there's something more, it's hinting to something more deeper. Again, some really nice papers on first one is on double slit, then on quantum eraser, and then the Nature Physics one is on this delayed choice quantum eraser, and the last paper again in Nature Physics is this recent paper where people have actually been able to demonstrate able to construct temporal double slit, a double slit in time, where future particles somehow knows what is going to happen to the past particles and adjusts its behavior accordingly. Interesting. That's why quantum mechanics is way more interesting than relativity. Now, it's possible to combine quantum mechanics and spatial theory of relativity into a consistent theory. Now, quantum mechanics is generally called a first quantized theory. Now, this is done through a process called second quantization. In second quantization, what is basically done is this, that you take an abstract mathematical object called a quantum field. Again, I can expand on it in question answer session. And you basically construct your quantum theory in terms of this abstract mathematical object called quantum field. Particles that we observe, material particles that we observe in nature, exist as approximations, as certain mathematical approximations produced by this quantum field. But this quantum field is more real than these material particles, because this approximation sometimes breaks. I mean, strictly speaking, material particles exist in flat space-time or in some very simple space-times where quantum field can have a certain kind of mathematical decomposition into material particles. So material particles are not really the building blocks of nature, quantum fields are. And that is why in quantum field theory, you can explain the creation of and annihilation of particles. Material particles can get created and annihilated. So basically, quantum field theory does to elementary particles what particle physics does to atoms. You see, when you had atoms as indivisible units of building blocks of the universe, at least in chemistry, that's how people thought about it in old times, till people discovered, no, these atoms are actually made up of electrons, protons, and neutrons, and this means that we can split atoms and produce different kind of atoms. In the same way, it was thought that maybe elementary particles, material particles are the building block of nature. Until we discovered, no, that's not actually true. Quantum fields are the building blocks of nature. And the material particles that we have are mathematical approximations produced by these quantum fields. And they can annihilate, they can create other particles, and they might not even be, it might not even be possible to have a definition of quantum fields in terms of particles in certain kind of spacetimes. So basically, also now this, and what kind of spacetimes it's not possible to have a definition of quantum fields in terms of material particles. Well, you can also do quantum field theory on a fixed spacetime. So spacetime is described by general relativity. It's not quantized. It's left as a classical spacetime. But you analyze quantum field theory on it. The quantum fields on this classical spacetime are quantized, obey quantum mechanics. The spacetime just remains there as something which is not, where you do not analyze the quantum effects on space and time. And this theory, where you do not analyze the quantum effects on space-time, but analyze quantum fields on this curved space-time described by general relativity, is called quantum field theory in curved space-time. It's a well-studied branch of physics. So first two books are really nice books on quantum field theory in flat space-time, which is how most people study quantum field theory. And if you are interested in quantum field theory in curved space-time, I thought I'll just put in two references for that too. Now, there are consequences of quantum field theory. I think the most evident consequence is that it ends materialism. Why? Well, you can already see from the previous slide, but let's go more into this. According to special relativity, there is an equivalence between mass and energy. In quantum mechanics, you can't really measure precisely the energy and time, which means that you cannot exactly say that there is no energy precisely at this time, because that's a precise statement, which implies that you can create a very small amount of energy, even though you start with no energy, for a very small amount of time. And this small amount of energy, because of mass energy equivalence, can convert itself into particles. And such particles are actually called virtual particles. Now you would say, well, they remain virtual, they exist only for a very small amount of time, except for the fact that there is an effect called dynamic Casimir effect, where these virtual particles become real. Not only that, Casimir effect has been experimentally observed. It doesn't just stop there. Like, look at this. The bare minimum requirement for something to be objectively real is that there should be intersubjective agreement on it. You and me should agree on something. Otherwise, this something is a gauge choices and is not fundamentally physical. It's a choice that I make. And this is really what we observe with particles. If you have two observers, one of them is accelerating with respect to another, and one of the observers, which is stationary, takes a box and observes that there are no particles in this box, no material particles at all. And the other observer